Greetings to all viewers. This is Professor Ankit Singh. We'll now move to the next topic, that is rigid pavements. Okay. In my previous class, we tried to understand the different layers that are present in a flexible pavement. Okay. Now we come to rigid pavements. Rigid pavements are those pavements whose surface is hard. Okay. So unlike the flexible pavement where the surface is flexible and even it does not show any rigidity, but here in the case of rigid pavements, the pavements will exhibit flexure. Okay, possesses noteworthy flexural strength and flexural rigidity. Okay, so basically you can say there is no elasticity in these types of pavements. Okay, made of Portland cement concrete, which could be either plain, reinforced or pre-stressed concrete. Rigid pavements have the slab action and are capable of transmitting the wheel load stresses through a wider area below. Okay, so in the case of flexible pavements, we observed that the load transfer was grain to grain. Okay, but here in the case of rigid pavements, the load transfer is through slab action. Okay, the load is transmitted through the area of the slab. Okay. Now in the types of construction part, okay, you can see what is the difference. This we have already studied once, but I'll repeat this again. Okay, so up to the sub base or the base course, it's the same. The subgrade, then the sub base, subgrade and sub base. Then the difference is between the bituminous layer over here, and here we are providing cement concrete, and if it is a reinforced with steel rods, it could be reinforced or it could be plain concrete or it could also be pre-stressed concrete. Okay, and here in this case we have a layer of bituminous concrete or asphaltic concrete, and to top it we have seal coat. Okay, so here there are basic differences based on properties in between flexible pavements and the rigid pavement. Okay, so design principle. In the flexible, it is an empirical method based on load distribution characteristics of the components. Okay, and in the rigid pavements, it is designed and analyzed by using elastic theory. So the design principles are different. The material here is a granular material. Okay, so different gradation of aggregates with a specified percentage of bitumen is being used over here. But in the case of rigid pavement, it is made out of cement concrete, which could be either plain, reinforced or pre-stressed. Then flexural strength. Flexible pavement will show low or negligible flexible. Sorry, this is flexural, okay, not flexible. It will show low or negligible flexural strength. Here, in the case of rigid pavement, associated with rigidity or flexural strength or slab action, so the load is distributed over a wide area of subgrade soil. Okay, so here it possesses flexural strength, here it does not possess flexural strength. Normal loading, here there is a chance of elastic deformation. Here there won't be any elastic deformation, since it will act as a beam or a cantilever, okay, or a slab. Under excessive loading conditions, there can be local depression in flexible pavements, and in the case of rigid pavements, cracks would be produced. Okay, because since this pavement cannot bend, cannot deflect, then if it is forced to do so, then cracks will be formed. Under stress conditions, the transmits vertical and compressive stresses to the lower layers. Okay, in the case of flexible payments. In case of rigid payments, tensile stress and temperature stresses are observed in the slabs, in the concrete slab. Design practice: constructed in a number of layers, flexible payments, and in case of rigid they are laid in slabs with steel reinforcement. Temperature: the temperature will not produce any stress in the case of flexible payments, okay, since they are allowed to expand or contract to some extent, okay, but in the case of rigid payments their stress is produced, okay. So temperature stresses are an important consideration in the case of rigid pavement. Force of friction: less deformation in the subgrade is not transferred, the force of friction is less, the deformation in the subgrade is not transferred to the upper layers. Here the friction force is high. The friction force is less in the case of flexible and friction force is high in the case of rigid. Opening to traffic: the flexible pavement can be opened to traffic in a quick time of around 24 hours, whereas for rigid pavements it cannot be opened by 14 days, okay, because concrete is being used and the time of setting and hydration is taken up, so a minimum of 14 days is required to open the road for traffic. Surfacing: rolling of the surfacing is needed here in this case, or in the case of flexible pavement, and rolling of the surfacing is not needed in the case of rigid pavements, okay, since we are casting using frames, okay. Now we'll move to pavement design. So a pavement design is a challenging job when you consider roads. The complex loading conditions exist, complex behavior under environmental conditions, and it is difficult in collecting information and modeling the performance of the road. So what are the different design pavement parameters that we need to consider? Pavement type, whether flexible or rigid or composite. What are the number of layers that we need to provide? What are the different materials that we use in each layer? What is the thickness of each layer? And in the case of rigid pavements, joint spacing and reinforcement, okay. So under vehicular loading, what are the things that we need to consider? What is the number or the volume of traffic or volume of vehicles? Vehicle type, okay, since there are different types of vehicles that are being used on the same road, hence we need to consider each type and then convert it to a standard unit and then use that value for design. Then what is the load carried? Load acting on the road through each of these type of vehicles would be different, okay. And what is the vehicular speed, whether it is stationary, slow moving or fast moving type of vehicle. Then there comes the climatic parameters, which include the rainfall and temperature. Under rainfall, total rainfall and seasonal distribution. Under temperature, the maximum temperatures, minimum temperatures, and also the daily or seasonal variations. Then under traffic loading conditions, this we have already discussed. So there are different types of vehicles that are in use, which are cycles, two-wheeler, passenger car, van, bus, multiple unit tractor and single unit tractor, etc. Okay. So there are different vehicle combinations or axle combinations that could be used for design. Okay, we have gone through this in the traffic engineering part. Okay, there could be vehicles having 3 axles, 4 axles, 5 axles, 6 axles, 7 axle, even 8 axle. Okay, So the load applied through each of these vehicles would be different. Factors for designing of pavements. So what are the factors that we need to consider while designing pavements? First one is design wheel load, then subgrade soil, climatic factors, pavement component materials, environment factors, and traffic characteristics. Under design wheel load. So it is obvious if the design wheel load is on the higher side, then the thickness of the pavement would increase. Okay. So higher the wheel load needs thicker pavements. Effects of static load on each wheel, multiple wheel load assembly, contact pressure and load repetition take into account. So under design wheel loads we need to take into account the contact pressure, the tire pressure, the load repetition, that is how many times the load is being repeated on the road. Okay, all these have to be taken into account. And as speed increases, rate of application of stress is also increased, resulting in reduction in the pavement deformation under the load. Okay, so with increasing speed, the deformation under the load would be less as compared to that of a slower moving or a stationary vehicle. At that point there would be more application of load. Then we have subgrade soil. A subgrade soil with low stability requires thicker pavement to protect it from traffic loads. Okay, so if the stability of the soil is less, if the shear strength or the bearing strength is less, then in that case we need to provide a thicker pavement to carry the loads. The performance of pavement depends on subgrade soil properties and the drainage. Okay, so drainage is also a major consideration, because with presence of water there are chances of swelling, and then if the temperature rise, then there is a chances of shrinkage. Okay, in these cases they might result in deflection and deformation, leading to formation of cracks, okay, or even potholes on the surface layers. Then we have climatic factors. Rainfall affects the moisture conditions in the subgrade and the pavement layers. Daily and seasonal variations in the temperature has significance in design and performance of the pavements. Freezing temperature, frost action considered in design stage itself. Okay, so here we have first one is the rainfall conditions which we need to consider. Okay, if the rainfall is more in that area, then we need to provide some provisions in order to protect our subgrade from intrusion of water. Okay, then there are daily and seasonal variations in temperature. These majorly affect the design of rigid pavements, because the concrete slabs, they tend to deflect when there is temperature change. Okay, and then freezing temperatures. At freezing temperatures, if there is presence of water in the subgrade or the subbase, then that water tends to freeze, and in that case after freezing the volume of water increases. Okay, and then again when the temperature goes to a higher side, then the ice formed again reduces into water, and hence there's a void that is created over there. Okay, due to this creation of void, there are chances of cracking in the pavements, and also there are chances of deformation when the loads are applied on that pavement. Pavement component materials. Stress distribution characteristic of pavements depend on the characteristics of the materials that are being used. Okay, there are different materials that we are using, which could be aggregate or different type of binders or different type of fillers. Okay, the durability of these materials under adverse conditions of weather should also be given due consideration. So we need to consider the durability factors which affect these materials. Then there are environmental factors. Height of embankment and its foundation details, depth of cutting, depth of subsurface water table, etc. would affect the performance of the pavement. Okay, so here majorly we need to consider the water table conditions. Okay, the water table from the subgrade should be at a minimum depth of around 1.2 meters. Okay. Now under design wheel loads, we need to consider a few factors. Various wheel load factors to be considered in design are maximum wheel load, contact pressure, dual or multiple wheel loads, equivalent single wheel load, and repetition of loads. Okay. Under maximum wheel load, the wheel load configurations are important to know the way in which the loads of a given vehicle are applied on the pavement surface. Okay, so wheel load configurations we need to find out first. What are the type of vehicles that are going to be traveling on the road? Okay, for highways, the maximum legal axle load as specified by IRC is 8170 kg or 8.17 tons. Okay, so this is the maximum load that is to be considered to be transferred through a single axle. Okay, converting it to a wheel. Okay, since two wheels are attached to a single axle with a maximum equivalent single wheel load of 4805. Okay, so through a single wheel 4085 kg is the maximum load that could be transferred, and through a axle the maximum load that can be transferred is 8170 kg. Now these loads have been specified by IRC. An axle is a central shaft for a rotating wheel or gear. So we have different axle combinations. Okay, in the case of single axle with single wheel, legal axle load would be 6 tons. With tandem axle, so in the tandem axle we have two axles, okay, which are connected in parallel. Here the legal axle load could be 18 tons. And for single axle with dual wheel, so there is single axle but two wheels on each side, legal axle load is 10 tons. And for tridem axle, so there are three axles over here, okay, with dual wheels on both the sides, the legal axle load, maximum legal axle load is 24 tons. Then we have different truck configurations. Okay, we have already seen this: two axle trucks, 5 axle, 4 axle. Okay, then we need to understand what is tire pressure. Okay, most of us already know what is tire pressure. It is the air pressure inside the tire. Okay, the pressure in an inflated rubber tube of tire is the tire pressure or inflation pressure. Then there is contact pressure. Contact pressure is a pressure or stress developed due to wheel load over the tire imprint area of the pavement surface. Okay, now since the load is being applied through the tire, we can calculate the stress at that intermediate section, at the junction between the tire and the surface of pavement. Okay, that stress is nothing but the contact pressure. Okay, so load on the wheel divided by the contact area, the area of contact between the tire and the pavement. This would give us the contact pressure. Then we have wheel load distributions for the two types of pavements. For rigid pavement it would be slab action, so the distribution would be like this. And here in the case of flexible pavement, since the load transfer is grain to grain and at an angle of 45 degrees, so it would be like this. Equivalent single wheel load or ESWL. Okay, this is a important concept. ESWL or equal vertical stress concept for ESWL. Okay, it is defined as the load on a single tire that will cause an equal magnitude of a pre-selected parameter stress, strain, deflection or distress at a given location within a specific pavement system to that resulting from a multiple wheel load at the same location within the pavement structure. Okay, so basically, to understand it in easy terms, okay, what we try to do is here we have a combination of wheels. Okay, so the load is being applied through these two wheels. Now what we need to do is we need to design a single wheel which can apply the same amount of load which is being applied through the combination of these two wheels. Okay, so equivalent single wheel which would transfer the same load which is in a combination of these wheels. Okay, so equivalence in terms of a selected parameter for a selected pavement and selected location. So equivalent single wheel load. Okay, here you can see for two wheels a single wheel will transfer the load, and here for four wheels a single wheel will transfer the load. Okay, so what is the factor using which we can convert the load transferred by these two wheels to this one wheel and by these four wheels to this one wheel? That is nothing but the concept of equivalent single wheel load. So equal maximum subgrade vertical stresses based on approximation of stress distribution in one layer. Okay, for a pavement thickness less than d by 2. Okay, firstly let us have a look at this figure now. Okay, consider this figure. Okay, there are two wheels here with a clear distance of small d and the center to center distance between the two wheels as s. Okay, and the load being applied through wheel 1 and 2 both are PD. Okay, so what the concept of ESWL says is for a pavement thickness less than d by 2 no stress overlaps. Okay, hence ESWL will be PD. It says that up to a depth of d by 2, okay, up to this depth, the load that is being transferred from each of these wheels are not overlapping. Okay, this is separate and this is separate. Okay, and what is the load that is being applied up to d by 2? It is nothing but PD. Okay, this is what it says. And at the depths of approximately 2 into s, the effect of overlap is such that it is equivalent to stress caused by 2p. Now after this point the forces here start to overlap. The load that is being transferred from this wheel and from this wheel will start to overlap in this section. Okay, so according to the concept up to the depth of 2s, okay, up to this depth the total load that is transferred is nothing but 2p. Okay, so at d by 2 depth the load transferred is PD and at 2s the load transferred is 2p. So for intermediate depths it is assumed that a linear relationship exists between load and thickness plotted on a log-log scale. Now what we can do is we can plot a graph using these values, taking depth along x-axis and ESWL or equivalent single wheel load along the y-axis. Okay, and we consider a log scale for this. So the values under the x-axis and y-axis both are in the log scale. So when you plot points for z equal to d by 2, the load would be p, so you have one point over here, and for depth equal to 2s, the load would be 2p, so you have one more point here. So when you join this point to this point with a straight line, now at any depth in between d by 2 and 2s, we will be able to find out what is the load acting at that depth, okay, using this graph. Okay, so this is the concept of ESWL. Also we have a formula. If we do not want to use this graph, then we have a formula. Log ESWL is equal to log of P plus 0.301 into log of 2z divided by t divided by log of 4 into s by d. Okay. Okay. Next we have a concept equivalent load factor. The ratio of damaging effect of non-standard axial load to the standard axial load. Okay, so the standard axial load is 80 kilonewton or 8170 kg that we already had a look at. Okay, 8170 kg, this is the standard load. So how do you find out the equivalent load factor? It is a ratio between the given load and the standard load, whole raised to 4th power. Okay, this is nothing but the relative damaging factor. Okay, it is also known as VDF or vehicle damage factor. So vehicle damage factor is given by the load acting divided by the standard load whole raised to 4. Now this VDF or relative damage factor is used while designing flexible pavements using IRC methods. Okay, so we'll next move to the flexible pavement design. I'll start with this in my next class. Thank you.